So good day, everyone. My name is Adolben Malabago Jr. of PS Math 1-B, and I'm here to discuss to you about Euclidean algorithm for subject fundamental concepts of mathematics. So Euclidean algorithm is something that you might already have encountered before during your elementary or your high school years. You would have probably heard this term, or at least used it when you were finding for the greatest common factor, or GCF, of between 2 to 3 numbers. And I'm sure GCF is more commonly taught in elementary, where Euclidean algorithm is discussed in the form of a technique rather than identifying it with its name. So before we get to proceed to Euclidean algorithm, let us tackle first about GCF. Now consider two positive integers, 18 and 84. So here we emphasize the word integers rather than numbers in this example. Now, let's find the greatest common factor of the two integers by checking their divisors or factors. And for this example, and for all the examples, let us dwell only on positive integers for now. So how do we get the GCF of the two given numbers? So the most usual way is by listing the divisors or factors of both numbers. Now, here we have the divisors of both 18 and 84. So checking all the positive divisors of both numbers, we have for 18, there is 1, 2, 3, 6, 9, 8, and 18. And for 84, there is 1, 2, 3, 4, 6, 7, 12, 14, 28, 42, and 84. And now, observe that the largest factor that is common to both numbers is 6. Thus, the greatest common factor of 18 and 84 is 6. So we were able to get the GCF of 18 and 84 through listing the divisors of both numbers. Now, let's have the definition of GCF. So here we have greatest common factor. The greatest common factor, GCF, or the greatest common divisor, is the largest factor or divisor that all numbers in a certain set share. Let D be the GCF of two positive integers A and B. In notation, the greatest common factor between two positive integers can be written as GCD of A and B equals to D, where A is greater than B and GCD stands for greatest common divisor. And hence, from the example earlier, the GCD of 84 and 18 is 6. So in the following slides, you will encounter this notation GCD with the open and closed parentheses in getting the GCF of greatest common divisor of two given integers. Finding the GCF between two positive integers can be done in other ways aside from listing both of its divisors, such as prime factorization. So here we have 18 equals 2 times 3 squared, which is also equal to quantity 2 times 3 times 3. And here we also have 84 equals 2 squared times 3 times 7, which is also equals to 2 times 3 quantity times 3 times 7. Or through visualization, which is shown here. Earlier, the GCD of 18 and 84 is 6. So here we have a number of boxes containing the number 6, which fits perfectly in the line of 84 and in the line of 18. So aside from listing the divisors, there is prime factorization and visualization as shown on this slide. But there is also another method. So aside from those methods, we can also use the concept of the Euclidean algorithm, or Euclid's division algorithm, in finding the greatest common divisor of two positive integers. This involves dividing using two positive integers, where the bigger number is a dividend and the smaller number is a divisor, and utilizing the remainder out of such numbers in determining the GCF or the greatest common factor. So to get the gist on how we are going to use the Euclidean algorithm, let's have an example. Consider two positive integers, 18 and 84, and use the Euclidean algorithm to find the value of GCD 84 and 18. So here, we will proceed with finding the GCF of both of these integers using the Euclidean algorithm. So let's start with dividing using the two numbers. So we have 84, 18, which is equals to 4, which has a remainder of 12. So here, the largest number will become dividend, and the smaller number will become the divisor. And since 84 is larger than 18, so 84 will be placed on the numerator here, and 18 will be placed in the denominator. So we have here, again, 84 divided by 18, which equals to 4 with a remainder of 12, since 18 times 5 will be more than 84, so we have to put 4 as the answer with the remainder 12. And since there is still a remainder, I will explain on the process in this Euclidean algorithm, or the remainder not equal to 0, we will use 18, the divisor, as the dividend, and 12, the remainder, as the divisor. So now we have 18 divided by 12 is equals to 1 with a remainder of 6. So here earlier 18 was placed in the denominator and acted as a divisor. And now since the remainder is not 0, which will be explained later on, 18 will be used as the dividend for the next set of division. So 18 will be placed on the numerator now, and the formed remainder, or the resulting remainder from earlier, which is 12, will become the divisor in the next set of division. So here 18 is placed on the numerator and 12 is placed on the denominator. So again, 18 divided by 12 is equals to 1 and still has a remainder of 6. Since the remainder is not yet 0, we will utilize 12 as a dividend and the remainder 6 as a divisor. And now we have 12 divided by 6 equals to 12 with a remainder of 0. So earlier, same as the process on the first set of division, 12, which was the divisor earlier, became a dividend in the next set of division. And now 6, which was the remainder earlier, became the divisor of this set of division. So 12 was placed on the numerator and 6 was placed on the denominator. And the resulting quotient of 12 and 6, is equals to 2 with no remainder. And now, since the remainder is now equal to 0, we will now declare the divisor 6 as our GCF. Hence, GCD of 84 and 18 is equals to 6, which we also got earlier from putting all the factors or the divisor of both of the numbers in the first example. So, the Euclidean algorithm is a technique for quickly finding the GCF or GCD of two integers. So this Euclidean algorithm involves a set of process where you're going to be repeatedly dividing numbers from the resulting divisors and the resulting remainders, depending on the given integer. So that is how we get the GCF of the two integers through the Euclidean algorithm. So this is basically one of the quickest ways to get the GCF between two integers. And now in order to know or understand completely what this Euclidean algorithm was all about, so let's have another example to get the gist of this algorithm. So this time, consider two positive integers, 12 and 32, and use Euclidean algorithm to find GCD of 32 and 12. So here we're going to repeat the process we did earlier with 18 and 84 and apply it here in finding the GCF of integers 12 and 32. So then we have, so since 32 is greater than 12, so 32 will be placed on the numerator, while 12 will be placed on the denominator. So here we have 32 divided by 12 is equals to 2 with a remainder of 8. And because it's not complete, we cannot divide completely 32 by 12. So there's a remainder there. And here we have the denominator 12 and the remainder 8, which we're going to be used on another set of division since the remainder is not yet 0. So here, the divisor in the first set of division 12 will be placed on the numerator, and while the remainder 8 will be placed on the denominator. So we have the resulting set of division 12 divided by 8, which is equals to 1 with a remainder of 4. And so since the remainder is still not 0, we will gonna get the divisor 18 and be placed on the numerator to become the dividend in the next set of division. But we will get the remainder 4 and place it on the denominator. So just like the process we did earlier as the concept of a Euclidean algorithm, which will be explained later. So we have here 8 divided by 4 is equals to 2, which has no remainder since it can be completely divided by 4. So since r is now equal to 0, or the remainder is now 0, the GCD of 32 and 12 is equals to 4. So if you see the first example earlier with the Euclidean algorithm, you observe that there we got 6 from the divisor of the latest set of division that we had earlier. So here, the answer here is 4, so we just got it from the divisor, which will be explained earlier as I explained the concept of the Euclidean algorithm. From the previous given, observe that the GCD of 32 and 12 is equals to the GCD of 12 and 8 and equals to the GCD of 8 and 4, which all equal to 4. And also the GCD of 84 and 18 is also equals to the GCD of 18 and 12, which is also equal to GCD of 12 and 6, which all equals to 6. So if you see these equations here, you would notice that these are the dividends and the divisors we encountered earlier in the previous two examples, the ones that we placed on the numerator and also the ones we placed on the denominator by pair. So investigating GCD of 32 and 12 equals GCD of 12 and 8, and the GCD of 84 and 18 equals the GCD of 18 and 12, we can see that the GCF of two positive integers is equal to the GCF of the smaller number of the integers, and the remainder when the larger integer is divided by the smaller number. So there is some sort of a pattern here that is shown in the previous two examples, and we will discuss it on the next slide through a lemma. So here we are now going to discuss about the technical part of the Euclidean algorithm. So here, the given observation satisfies the following lemma related to the Euclidean algorithm, which we referred to the pattern we saw from the previous slide. So we have here a lemma, which is related to a theorem. If a and b are positive integers such that a is equals to qb plus r, well, where r is less than b but greater than or equal to 0, then the GCD of a and b is equals to the GCD of b and r. So the formula GCD is basically the notation of the observation we had with the dividend and divisor of the two previous examples that we saw by pair, which we placed on the numerator and the denominator. So basically this is the equation that represents the observation we had earlier. So for the following slides, we will check and apply the following theorems to understand the concept of Euclidean algorithm. So there are going to be theorems that are going to be introduced in this slide, which we're going to use in explaining what the Euclidean algorithm is all about. So here are some important theorems, definitions that will be utilized in the next few slides to emphasize the structure of the Euclidean algorithm. So we have here the first theorem, which is called the division algorithm. So here we have let a and b greater than 1 be integers. Then there exist unique integers q and r such that a is equals to bq plus r, where r is less than b but greater than or equal to 0. And here we also have another theorem. We have here some basic properties of divisibility. So here we have 3 from sub-theorems here. So suppose that a is not equal to 0 and b is also not equal to 0. If a divides b and b divides c, then a divides c. So here the vertical line that is in this theorem, which reads as divides. So here I pronounce it as a divides b, b divides c, and a divides c. So that's how we read the notation. So for the second sub-theorem, suppose a is not equal to 0. If a divides b and a divides c, then A divides the quantity bx plus cy for any integer x and y. And here we have the third subtheorem. Suppose A is not equal to 0 and B is not equal to 0. If A divides B and B divides A, then A is equals to positive negative 3. So these theorems revolve around the concepts of integers that is widely used in mathematics. So now here is the definition of the GCD, or greatest common divisor, or the GCF, with the use of variables as integers. So here, the formal definition is of the GCD is a non-zero integer d is said to be the greatest common divisor, or the GCD, of A and B if 1, d is a common divisor of A and B, and if C is a common divisor of A and B, then C is a divisor of N. And now let's first prove the stated lemma using the stated theorems to provide a flow in understanding the concept of Euclidean algorithm. So we have here the stated lemma earlier from the previous slide. So if A and B are positive integers, such that A equals QB plus R, where R is less than B but greater than or equal to 0, then GCD of A and B is equals to GCD of B and R. So here we have the following proof with the theorems we introduced earlier. So here, let D be equals to GCD of A and B, and E be equals to GCD of B and R. By the formal definition of the greatest common denominator, or GCD, D divides A, D divides B, and D divides QB. And by the division algorithm, R is equals to A minus QB. By the sub-theorem 2 of the basic properties of divisibility, D divides R. Now, D is the common divisor of B and R. And since E is equals to GCD of B and R, E is also the common divisor of B and R. That is, E divides B and E divides R. By sub-theorem 1 of the basic properties of divisibility, D divides E and E divides D. By sub-theorem 3 of the basic properties of divisibility, D is now equal to E. And the proof ends here. So now, suppose we are finding for the greatest common divisor of the two positive integers A and B using Euclidean algorithm. So here, it's like we are getting the GCF of two integers, but through the use of notations. So here, we know that by division algorithm that for positive integers A and B, let's say in this case A is greater than B, A is equals to QB plus R, where R is less than B, but greater than or equal to 0. From the division algorithm, if A is divided by B, then Q will be the quotient and R will be the remainder. That is, A over B is equals to Q with the remainder R. So the division algorithm formula we read is related to just how we solve the Euclidean algorithm. It is one of the important properties in integers, especially in the concepts of mathematics, the division algorithm. So here, the formula is manipulated, or should we say observed, to mimic how we solved earlier for GCF with the use of variables instead of numbers. So here, QB, if we divided it by B, it results to Q, which basically is the quotient of A over B, with R as the remainder. So that's basically the element of the division algorithm. It revolves around that concept. So now we will utilize these variables to find the GCD of A and B. Suppose we divide A by B, getting our first quotient and first remainder, Q sub 1 and R sub 1 respectively. So here, instead of using numbers, we use notations or variables to represent those numbers, unlike the previous examples, since it's can be computed. And so here we're just only going to explore how the Euclidean algorithm works in terms of notations or its theoretical aspect. So here, A divided by B is equals to Q sub 1 with remainder R sub 1, where R sub 1 is less than B and greater than or equal to 0. So if you observe that we apply the elements of the division algorithm here, so it's being applied to demonstrate the Euclidean algorithm through the use of notations. So here, if r sub 1 is not equal to 0, we will now divide b by r sub 1, getting our second quotient and second remainder. So here we have, I mentioned about first and second quotient. So this order is reflected on the subscripts of the cube or the quotient and the remainder as shown in this slide. So here we have now b earlier was the divisor, so now it becomes the dividend, similar to the previous examples, and the remainder, or the first remainder, now became the divisor of the next set of division. So here we have b divided by r sub 1, which is equals to the second quotient, which we don't know because we did not place any value, but let's assume that that is the second quotient, which will surely be different from the first quotient, with the remainder r sub 2, which is the second remainder that we get, where r sub 2 is less than r sub 1, and is greater than or equal to 0, which we reflected from the division algorithm. And now, if r sub 2 is not still equal to 0, the same process will occur. So the r sub 1, which was on a divisor, will become, or now will be placed in a numerator as a dividend, while the resulting remainder earlier, which was r sub 2, will be placed on the denominator. And in dividing those numbers will yield a third quotient, which is q sub 3, and as well as a third remainder, r sub 3, where r sub 3 is less than r sub 2 and is greater than or equal to 0. Now here is the continuation from the previous slide. So here, from the last slide, r sub 3 is not equal to 0. And if r sub 3 is not equal to 0, then we proceed with another set of division where r sub 2, which was from the divisor before, became the dividend and was placed in the numerator. And then the yielded remainder from the last set of division became the divisor of the next division, yielding the fourth quotient and the fourth remainder of this given set of divisions that we had so far, until we got the fifth, and we got fifth quotient and fifth remainder, and so on and so forth. And now we have a condition here that suppose the remainder gets to 0 when getting the k plus 1 quotient. So here we use the arbitrary constant k to represent the last of the numbers, since positive integers are infinite in size. So at some point we need to stop, and we need to stop at a certain point in order to continue with our solution. So we settled the condition with the k plus 1 quotient, and so here after 5 we had after the fifth quotient and remainder we had the ellipsis here, and so we proceed with if r sub k minus 1 is not equal to 0, then we have r sub k minus 2 over r sub k minus 1 equals to quotient sub k and r sub k, where r sub k is less than r sub k minus 1 and greater than or equal to 0. And thus we have the final form on getting the k plus 1 quotient. So here, if r sub k is not equal to 0, then r sub k minus 1 over r sub k is equals to q sub k plus 1. So we have a remainder of 0 where 0 is less than r sub k. So that is our final form of set of divisions. We know from the lemma we proved earlier that GCD of AB is equals to the GCD of PR, which involves the remainder. Now, if we are going to continue to prove the said lemma involving the succeeding sets of dividends and divisors, while finding the GCD of positive integers a and b, assuming that the remainder will be 0 on k plus 1 attempted, which we had in the previous slide, we will know that the GCD of A and B is equal to the GCD of B and R sub 1, and then is also equal to GCD of R sub 1 and R sub 2, and is equal to the GCD of R sub 2 and R sub 3, and is equals to GCD of R sub 3 R sub 4, and equals to GCD of R sub 4 R sub 5. Here we have an array of GCD of 2 integers, which we had as our analyzation from the examples. So we applied it here, that is continuous to the next slide. So in this slide, we ended on the GCD of Rk minus 1 and R sub k. So that's basically the last array that we're going to put there, which we applied from our previous observations from the previous examples, which resulted to this. And notice that from the last set of the equation we got from the last set of divisions, we have sub k minus 1 over r sub k is equals to r sub k plus 1. And here we have r sub k minus 1 is equals to r sub k plus 1 and r sub k. So that is the equation that we have. And since r sub k is the only common factor between r sub k minus 1 and r sub k, it follows that the greatest common factor of r sub k minus 1 and r sub k is r sub k. That is the GCD of r sub k minus 1, and r sub k is equals to r sub k. And hence, the GCD of the two positive integers a and b is equals to the GCD of r k minus 1 and r sub k, which is all equal to r sub k. So we got here the GCF of the two positive integers earlier, a and b, where we demonstrated the use of Euclidean algorithm in notation. From the previous examples, we have the following GCFs. So here we have a GCD of A and B, which is equals to the GCD of R sub k minus 1 and R sub k, which is all equal to k. And all equal to R sub k, I mean. And here we also have the GCD of 32 and 12 is equals to GCD of 8 and 4, which is equals to 4, which we got from the example earlier. And here we also have the GCD of 84 and 18, which is equal to GCD of 12 and 6, which is equals to 6. So we compare the results of the first two examples earlier and the example we had with positive integers a and b. And so observe that as we perform division from the two positive integers to the accumulated remainders, we eventually reach to the point where the two numbers will have no remainder, with the smallest number or the final divisor as a GCF of the two given integers, which we justified with the use of theorems and definitions. Likewise, the GCF of two positive integers can be found through the repeated application of the division algorithm. So that is a long explanation on the theoretical concept of the Euclidean algorithm, which is quite tedious for just finding the GCF of two positive integers, but with a heavier purpose and a role of the methods. So there is an extended version of the Euclidean algorithm here as a theorem, but we will not going to go deep in its theoretical aspects, but at least we can see that there is an extension of pattern to the algorithm. So here, the theorem of the extended Euclidean algorithm states that let a and b be two integers such that not both are 0. Then GCD of a and b exist. Moreover, if d is equals to GCD of a and b, then there exist integers s and t such that d is equals to sa plus tb. So let's see the examples here. So we have here 6 equals the GCD of 24 and 18, which is equals to 1 times 24 plus negative 1 times 18. Another here we have 2 equals GCD of 50 and 36, which is equals to 7 times 36 minus 5 times 50. And here, the last example, we have 4 is equals to the GCD of 32 and 12, which is equals to negative 1 and 32 times 32 plus 3 times 12. So here, the integers that represent a and b are also present in the other side of the equation. So we can see the beauty of the pattern and the pattern from the theorem stated here in the actual examples. So from the discussion of the Euclidean algorithm, from some of the examples and its theoretical concept, here are the steps in getting the GCF of two integers using such algorithm. So here, for step 1, we have given two positive integers, say a and b, or any two numbers. Divide the larger integer by the smaller integer. So you first have to identify which is larger and which is smaller, and then the larger will become the dividend of the division, while the smaller one will become the divisor, and you will get the quotient of both of the numbers as well as its remainder, which will be applied here in step 2. In step 2, we have to identify the remainder of the two integers. If the remainder r is not equal to 0, divide the smaller integer by r. So this is similar to what we demonstrated in the previous examples, as well as the one with the theoretical aspect. So if the r is not equal to 0 in the initial division, the remainder will become the divisor in the next set of division, with the smaller integer being the dividend of the next set of division. So the smaller number or the smaller integer will be placed on the numerator while the remainder will be placed on the denominator, and so on and so forth. Step 3, if a non-zero remainder persists, continue dividing with the remainder as a divisor and the smaller number of the previous division as the dividend until r becomes 0. So the process is just in cycle until the remainder will become 0. So if the remainder is not equal to 0, that remainder will be used to be the divisor of the next set of division, while the smaller number of the previous set of division will become the numerator. So it's a process until r will become 0. And here for step 4, if r is equals to 0, from the final dividend and divisor, say n and n, then n is the GCF of the two positive integers. So basically, if this n was the final divisor of the set of divisions that we had from the previous examples, and with the notation that we had from the theoretical aspect of the Euclidean algorithm, we see that the answer is found on the divisor of the final set of divisions. So that's basically the principle of the Euclidean algorithm here, which that is the GCD of A, B, which we represent the two positive integers, is equal to n. Now, again, n is the final divisor of the set of divisions that we had from the first division, or from the first computation from the first two positive integers. So after the discussions, so let's try this out in the short activity below. So here are the directions. Find the GCF of the sets of two positive integers below using the Euclidean algorithm. So we have 5 items here. One is 36 and 98, 25 and 85, 69 and 102. Here we have 133 and 108, and 438 and 125. So using the Euclidean algorithm, we need to find the GCF of these sets of two positive integers here. And there's a bonus question below. Now, for any a that is an integer, what is GCD of a and 0? And there you also have to explain why is the answer. Now, the question below is actually one of the properties of the Euclidean algorithm involving the number 0, and you have to figure this one out on your own. So that's all for the discussion, and I hope you learned a lot in this presentation. If you have some confusions, feel free to go back to where you were confused at and check on the slides in order for you to understand. So thank you for listening as always, and God bless.